Hello and welcome to Tattva Deep, conversations and explorations. For our 6th episode on physics, we sat down with Professor Dean Rickles. He's Professor of History and Philosophy of Modern Physics at the University of Sydney, Australia, where he's also Director of the Sydney Centre for Time. He's the author of many books, including Life is Short, appropriately brief guide to making it more meaningful, covered with Deep Mist, the development of quantum gravity, and a brief history of string theory, from dual models to M-theory. He's co-editor with Elaine Landry of the Routledge Studies in the Philosophy of Mathematics and Physics book series. This was the first ever 2-part conversation series on Tattva Deep, and I'm truly grateful to Professor Rickles to grant us his time graciously. I'm also grateful for his articulation and clarity of thought on such topics as why physics needs philosophy and why some physicists might feel otherwise, the big mystery of why there is something rather than nothing, and also what the presence of a quantum realm means to him. We hope this conversation can help the listeners see the tattva, or the true essence of physics, and the important role it plays in helping us understand the world we live in and appreciate the fundamental forces that lie underneath everything. Hello, Professor Rickles. Welcome to Tattva Deep. The first, I'd just like to get started with my guests without wasting any time. So I've prepared a bunch of questions for you. And the first question I would like to ask you is, what can you say is the difference between a philosopher and a philosopher of physics? And what would you say are the similarities?
Well, I mean, a philosopher of physics is basically analyzing their attention on one specific way of gaining knowledge about the world, i.e. physics. So it's usually not, it doesn't really help with the construction of physics. It takes the final products that physicists produce and it analyzes their assumptions and their foundations, which often physicists don't do themselves. They will produce a theory, they will look at the kind of experimental predictions it makes, they will compare the numbers from the experiment with the numbers that the theory itself is generating. They won't go beyond that very much. But the philosophers are sort of probing whether the claims of physicists are necessarily true, whether there are multiple ways of making sense of the experimental results that are coming in, what the theory is saying about the structure of reality, what it's saying about the objects, the kinds of objects that exist, especially what it says about space, time, matter, and causality. A philosopher is just somebody who looks at the world in a more general way, I suppose. They wouldn't restrict themselves to one particular way of gaining knowledge of the world. They would look at things like the knowledge acquisition process itself. They would look at, what kind of, how we justify our knowledge claims about the world. They would look at things like properties in general, what kind of thing a property is, what kind of thing a universal is, what kind of thing causality is, rather than saying, what does this theory say about causality? So philosophy is sort of one, you could either say it's one level deeper or it's one level higher, but it's more general than a philosophy of physics.
By general, would you also mean, sorry, go on, sorry.
Well, I was going to say, I mean, the way I prefer to view philosophy of physics is more like what used to be called natural philosophy, where you're applying the principles of philosophy to nature and the understanding of nature. And I think I quite like the expression natural philosophy and wish it would return, really.
So yeah, okay. So you use these 4 words, if I heard them correctly and wrote them down correctly. Space, time, matter, causality are essentially the things that philosophers of physics study in terms of the theories that the physicists are proposing. So are these also then essentially the subjects that the philosophers in general are studying, and will probably have a slightly more elaborative view on these things?
In general, yes. If you're looking at metaphysics, if you're looking at specific areas of philosophy itself, so there's things like metaphysics, which is the study of being generally, which will include physics, but also consciousness and things like that. Or there's the study of ontology, which is what we're talking about here. Ontology is the study of what kinds of things exist in the world, what there is in the world. And that usually gets pinned down to space, time, and matter, and the relationships holding between the material constituents.
Then would it be right to say that philosophy of physics is an offshoot of physics? Or did it emerge, would you say, alongside it?
That's a very tricky question. I mean, in the olden days, there wasn't really these kinds of divisions.
Right.
We didn't have. I mean, I suppose Aristotle was probably the first to start creating divisions in the subject matter of philosophy and the sciences, in fact, and talking about biology and astronomy, the study of the heavens, metaphysics, physics. So he was trying to categorize the different branches of knowledge. Before then, I mean, it's hard to speak of philosophy or physics before then. They're so sort of tightly interwoven. Yeah. And then even later on, people like Isaac Newton and Descartes, they were as much physicists and general scientists as they were philosophers. So this is why I like the expression natural philosophy a lot better. But in the modern period, the philosophy of physics is definitely a specialization of philosophy, just like we now have philosophy of biology and philosophy of psychology, and now philosophy of artificial intelligence. There's ever more specific subdivisions that seem to be happening.
Right.
And of course, you can even within philosophy of physics subdivide further, and you can be a philosopher of quantum mechanics or a philosopher of space-time physics.
Okay. One reason for this, for someone like me, a commonsensical reason for this would be that the subjects itself are so vast. So there is someone who's studying quantum realm, and there are subdivisions in that as well. So because the subject itself is so vast, even if one person or a group of individuals are devoting their entire lifetimes to it, it just keeps on growing. So in that way, it makes sense for the subdivisions. But perhaps what ends up happening is that the divisions don't end up interacting with themselves. So is there a gain from the knowledge that each is acquiring, or is there a loss because they are not interacting?
Well, probably both. I mean, there's a gain in that you're getting deeper specific knowledge in one sense. You're learning more and more about some specific phenomena, for example. And then there's a loss in that you're not getting this. So you're getting a gain in the vertical sense. You're going deeper, but you're losing in the horizontal sense in seeing the interconnections between the various subjects. So you have people who will entirely forget or ignore the fact that there's consciousness in the world, and they will be studying one particular branch of physics, and so some entire branch of knowledge will be excluded and bracketed out when it might not be sensible to do that, or bits of biology or something like that. It might not be sensible to exclude them because they might actually be playing a role, and then you will never discover potential new phenomena that involve the interaction between the disciplines.
Right.
I mean, it seems to be that this is breaking down a bit lately, this idea of the siloing of knowledge, so that there are just people in this department who only study one particular subject. I mean, the big thing now, especially if you're applying for a grant, say, is that you should focus on interdisciplinarity and look at how there's cross-pollination going on between various disciplines.
It makes sense, yeah. So, yeah, so I was watching one of Mr. Carlo Rovelli's lecture, and the lecture was titled "Why Physics Needs Philosophy." So he was presenting two sides, and then he had his own opinion on books. So one is there are a bunch of people who said it's unnecessary, it's useless. We don't philosophy does physics does not need its own philosophy. It's even dangerous. So there are people who claim that from the community, and of course then there are those who say no, it's important, it adds value. And people like Einstein and they believed in the philosophy of physics. What do you think are some of the reasons that people oppose it? And then people like Einstein seem to value it. And I think Mr. Rovelli also. Yeah.
I mean, I'm not sure that Einstein promoted philosophy of physics. He was a physicist who was also aware of philosophy, and it had an impact on him. He wasn't doing philosophy of physics as such. He was using philosophy to help him construct his physical theories. So especially sort of David Hume's analysis of causality, for example, the idea that there's not really any such thing in the world as causality, like heavily influenced Einstein when he's creating his special theory of relativity, and he admits this. He's often talking about Spinoza and Kant, and you can see elements of this in his general theory of relativity. So he was certainly heavily influenced by it, and you could probably say it was essential for him being able to do the kind of revolutionary work that he did, because you need to, I mean, in order to do revolutionary work in physics, you're obviously questioning the foundations. And to question the foundations, you're probing exactly these categories of space, time, and matter that I mentioned, and causality that I mentioned earlier. That's how you get revolutionary physics. But it's not doing philosophy of physics in that case. The reason why, I mean, I'm not sure exactly when it happened, when people started going against the idea of philosophy in the sciences and philosophy in physics. It's probably something to do with logical positivism, which was something that came out of philosophy itself. So there was a whole bunch of people like Moritz Schlick and Carnap and others who were against the idea of metaphysics because it couldn't be tested. So then you get this whole idea of, you have to have something that's testable, otherwise it's kind of worthless. But then if the physicists are dealing only with testable things, they don't really need this extra framework of philosophy. So the main physicist who's associated with this extreme anti-philosophy position is Feynman. Of course, you probably know this, Richard Feynman, who says things like, philosophy is about as useful to philosophers as ornithology is to birds. And he's got a whole bunch of these kind of nice sounding quotes where he's heavily against philosophers, and he just thinks you just should calculate. You need to shut up and calculate. And because he's such a sort of charismatic figure, I think this sort of spread into even into the present generation of physicists who think it's cool to be anti-philosophy and just like focus on the mathematics and do computations. And I don't know why it would be dangerous. Maybe it's dangerous because it would mean that you would never find yourself doing ordinary everyday science. And at some point you need to allow things to settle in order to generate new results and generate new phenomena and generate new discoveries within a paradigm. So Kuhn famously has this idea of paradigm shifts and normal science. So you have revolutionary science and then you have a period of normal science. And you can't just have constant revolution all the time. That would be sort of impossible. You'd have no science at all. The point is, if you are constantly questioning the foundational aspects, you're never gonna allow the discipline of physics to get into a stage where you're just probing what you have. You're always going to be trying to change it for a new theory. So, I mean, you can see that there are genuine dangers with having every physicist also be a philosopher. I mean, it's not really practical to have a discipline like that. So it's not reasonable.
Right.
I think and I think Rovelli, I mean, remember that Rovelli is working on a revolutionary science. He's working on quantum gravity. So from his point of view, that for this kind of philosophical thinking where you're questioning the foundations is vital, because what he's doing is pointing out that there are incompletenesses in the foundations of general relativity and quantum theory. There's inconsistency in their foundations. So either one or the other has some kind of flaw, is incomplete in some way, or needs some kind of modification. And Rovelli thinks that the kind of modifications that's going to be needed to get a theory of quantum gravity, where we're merging general relativity and quantum mechanics, is a philosophical one. It's one of these old-fashioned kinds of revisions where you're just changing what you mean by space and time. And in the case of his own approach, loop quantum gravity, he ends up saying that possibly these things don't even exist at a fundamental level.
Right.
You don't have space and time at a fundamental level.
Right. Yeah. And like you just said, that what Mr. Rovelli is trying to show is that there is incompleteness. So there is in the foundations of these two parts of physics, that have, so there are holes to be filled, gaps to be filled. So this is one reason why philosophy is important. I remember speaking to Dr. Mark Gallagher, and he said that he gave the example of set theory. Now, I don't remember the example very well, the intricacies of the example, the detail of what he said, but he said that at some point, mathematicians were walking down a certain road, and which was incorrect because it was proven by philosophers to be so. And that helped when you have philosophy involved in, or when you're working in tandem with a philosopher. I don't know how it works. Like, is a physicist developing a theory independently or in a group, whatever, and then they present it, and then the philosopher steps in and says, okay, now let's reconsider some of the premise, let's reconsider some of the insights, let's reconsider where we are going from here. I don't know how that happens also, because I come from advertising, me and my husband both, and I was a writer, a copywriter. So we always worked with the designer. So it was a continuous collaboration on every project, because there was a lot of back and forth. But it's a similar. We were part of the same thing. Here philosophy and physics is kind of its own discipline also. So I think what I'm trying to ask you is, so for Dr. Mark Gallagher, it has a very practical value. It helps the discipline itself save time by keeping the physicist walk down the wrong road of thought, if nothing else. And you're saying it also will help, coming from how Mr. Rovelli is seeing it, it can also help you fill in certain holes, which are keeping the quantum gravity and all of these things in a maybe from progressing or from flourishing in a more full manner. So are there some other aspects that philosophy is then bringing to physics, which can help physicists probably take it seriously, the ones who are kind of opposing its presence altogether?
Yeah. So in the case of Rovelli's subject, quantum gravity, I think this was a kind of act of desperation to look towards philosophy, just given the length of time that people have been trying to find this theory. In the initial days, it was about as unphilosophical as it's possible to be. They were treating it exactly like any other theory, any other quantum theory, trying to quantize it as they did with the electromagnetic field. And things kept going wrong, and the mathematics kept getting harder and harder. And then it came to a point, probably in the 70s,
right,
where it was realized there was something different about this particular problem, because of the fact that general relativity is a theory of space-time as well as a theory of gravity.
Mm-hmm.
So there was something different. It wasn't quite as easy as when you're quantizing the electromagnetic field, which is just, a field that exists on a stationary background space-time.
Right.
Because of the nature of general relativity, which says that there's no background space-time, that you have to solve equations in order to work out what space-time is, what its structure is. there's more of a challenge in them quantizing that theory, because it's the theory of space-time. So quantum gravity is a theory of quantum space-time, basically, as much as it's a theory of quantum gravity. So it was a sort of recognition of the special features of gravity and general relativity that led people down this path of having, for example, joint conferences with philosophers and physicists suddenly. So there's this famous conference called the Osgood Hill Conference that happened in, I should know this because I wrote a book on the history of quantum gravity. It was somewhere in the, I think it was in 77 or 78, where you have collaborations and you have philosophers giving talks on quantum gravity as well as physicists giving talks on quantum gravity, realizing that they're dealing with the same kinds of problems, i.e., how are we to understand the physical picture of general relativity and the physical picture of space-time, what it tells us about the nature of observables, and especially whether the observables in the space-time are inherently relational. So we have to have these relational field theories, and then it's from that point it goes down this more philosophical path. But there's also a branching that happens, because those quantum gravity folks that are more interested in general relativity, in the gravitation side, are the ones who are more attracted to philosophy and working with philosophers.
Right.
Those that are on the particle physics, quantum field theory side are still not really into these collaborations with philosophers, because they are still dealing with the idea that theories of physics are just particles moving around on fixed space-time, and we're looking at and then we quantize these as fields on flat space-time. So they're still not really gotten into the special features of general relativity, because they're not general relativists, they're particle theorists and quantum field theorists. So we end up with a split like this, where one side doesn't like philosophy still, and the other side now thinks that we need philosophy because it's the same kind of problem. It's a philosophical problem,
Right.
Solving the problem of quantum gravity.
Right. So if you're looking at it from these two places, it seems that one has come to understand the need for philosophy. One is probably yet to come to a place where they feel like now we need some philosophers to step in, because, yeah.
Yeah.
Okay.
Yeah. They're not there yet, although possibly there's an ever so slight shift lately in string theory, where they're realizing that a lot of the things that were being said about the relational nature of observables in quantum gravity also applies in string theory, in their view, as well. So it looks like there's some strangeness going on in their view as well, which might require some kind of philosophical contribution as well. And yeah, exactly. And I've edited, I've organized conferences myself and edited things where we've had string theorists as well, who are writing for a philosophical audience and trying to think about the philosophical nature. But this is very recent development, and it's still sporadic.
Sure. So you used the term earlier, natural philosophy, natural, and physics itself, the word translates to natural, maybe physical. I think with time it has also, the meaning of the word physics itself has changed. And we had one philosopher of physics as a guest earlier, Dr. Tim Maudlin, and I did ask him, do you think that that physics then is a way of looking, and then it's also a matter of what it is looking at, and then it's also a matter of how is it looking at it. So before we decide what the result is, there seem to be three precursors to in terms of approach that you have towards the problem that you're looking at. So I'm not asking you about physical or natural. What I want to learn from you is that if physics is about understanding reality, am I right in saying that?
Well, some people would say you are right. I don't think it's about explaining reality. I think it's about explaining the empirical world.
Test
And if you assume that the empirical world is all there is, then you will agree that physics is about describing reality as well. If you think that there's more to reality than the empirical world, then you would disagree with that.
Yeah.
So it depends on your stance, whether you think there's something beyond what we observe, beyond mere observation, something deeper.
Okay, so if coming from where you're coming from, if the empirical evidence is all there is, and that's then what constitutes reality, what would you say are the parameters that define reality?
Well, I mean, I don't agree that the empirical world is all there is, but if I did, then I would say that the parameters that define, I mean, at the root of physics and how it works are principles of symmetry, right? You're looking for all of those things that stay invariant under certain transformations and operations. And then your view of reality is that we can be realist and we can believe in those things that stay the same regardless of these kinds of transformations, regardless of where we do the experiment, how fast we're going, how strong the gravitational field is that we're in. Do we still get the same result over and over again? If so, then that's a solid result and that's part of reality. So that's basically the methodology of physics, as I see it, is you're searching for invariance and symmetry principles in order to get a grip on the stable structure of the universe.
Invariant.
You're not so much.
So sorry,
Go on.
unchanging, right?
Yeah.
Something that remains as it is, as was first ever seen, and then despite all the changes around it, it itself manages to stay the same. That's the evidence of, yeah.
Yeah, you're looking for something that's robust under interventions of various kinds. It's the same methodology as when you do a medical experiment, right? A randomized trial or something. You're looking at you're trying to find the robust phenomenon underneath a whole bunch of other changes that are being carried out, right? And it's the invariant thing that's the real thing. So you have an invariant view of reality, basically. And this was associated with many people like Hermann Weyl. Einstein's view was basically the real is that which is invariant under all of the coordinate transformations and the other kind of transformations.
And then what I find interesting also is that what we might consider invariant, like unchanging for say 2000 years or 150 years or 500 years, could still come under attack at some point. Something might emerge that could challenge it. So that also happens, right? So do then philosophers and physicists keep this in mind, that they probably are unable to commit to something wholly because of this? And is that a good thing then?
Well, I mean, it's a good thing that they're open-minded about the fact that we might not necessarily have the final story, even on things like maybe you're referring to constants of nature. So there are some theories. I mean, Paul Dirac had a theory towards the end of his life that the gravitational constant might change over time, might not be the same strength. And there's a few theories along these lines. I think James Webb has a view, an Australian, who has a view that the constants of nature might change and evolve over time, so they're not constant at all. It's a sort of almost an environmental effect,
right?
And this is sort of I suppose this becomes connected to the anthropic principle. The reason that these constants have the values that they do right now is because, well, if they didn't, we wouldn't be here, because of the fact that they provide a basis for complex structures to emerge and things like this. But it doesn't necessarily mean that they have to be like that or they're going to stay like that. If you think that the empirical encapsulates what is real, then I think that the way you go about that is to look for the invariant structures. But that's only if you think that the empirical world is real. I mean, my own view would be that if you want to explain things in the empirical world, then you should look beyond the empirical world for explanations. It's very hard to explain explain what you're trying to explain using the very things that you want to explain, i.e. bits of the empirical world. That seems sort of like a misguided venture, which is why you have philosophy that goes a little bit deeper under those structures.
Right. What would you say are some of the biggest questions that physics or physicists have ever asked? And more importantly for us, which of these questions would you say, and perhaps the answers that have been found to these questions that have shaped the way we think as a collective, as a race?
Well, I mean, obviously we have the question of whether the universe had a beginning or not, which shapes us as a race because it links into all sorts of other obvious theological issues. So if the universe began, then it leaves a bit more space for the idea of a creator that, triggered the bang. I mean, there was a huge debate in the early days of Big Bang cosmology over whether it was a necessary way of explaining the expansion of the universe. So there was another competing theory known as the steady state theory, which was developed by Hermann Bondi, Fred Hoyle. There were others who were working on it, like Felix Pirani and so on. And the idea was that they didn't want an origin. So what they wanted instead was an eternal universe. So there was this eternal creation, this steady state creation model, where new space is just continually being created. And that's what explains the expansion. And the reason that they adopted this theory was, in fact, partially theological. They didn't want any space for a creator. So I had this directly from an interview I did of Felix Pirani, who was the guy who came up with a theory of the modern theory of gravitational radiation and how we detect it. And he was a steady state person, precisely because he didn't like the Big Bang, precisely because it gave too much scope for creation. And obviously the person who came up with this idea, the idea that there was a Big Bang, was a Catholic priest from MIT.
Wow, okay. Okay.
Lemaitre.
Okay.
Lemaitre, sorry. Lemaitre.
Okay.
So that obviously has a huge impact. I mean, it's usually the cosmological questions are always going to have ramifications like this. If we're dealing with the big issues, the structure, the age of the universe, and these kind of things, they're always going to have ramifications for our broader worldview. Other examples are obviously to do with the nature of space and time, whether they exist, whether it's discrete or not. If it's discrete, well, then you have a smallest possible bound to what's possible in terms of things like information and processing. So it automatically, if your space is finite, then it automatically limits you in various ways of what you can do in the universe. Whereas if it's continuous, it doesn't. You can imagine ever increasing your processing power or things like that. So there's all sorts of very direct ways in which what look like philosophical big questions will have some direct impact on, on our lives, on ordinary people, and these kinds of issues, I think.
You wouldn't say, who are we? What are we doing? How do we get here? These are not the questions that the domain of physics is, forget answering, but asking.
Well, they do. I mean, one of my projects at the moment is the question of why there's something rather than nothing. And physicists have had a go at this. I mean, Lawrence Krauss, don't know if you know Lawrence Krauss, has a book where he claims to have solved the problem using nothing but physics of why there's something rather than nothing. So he's a very good example of somebody who's very anti-philosophy and acts like the new kind of Feynman, So he thinks we can solve the problem of why there's something rather than nothing without involving philosophers, and it's just a physics problem. And he says, the way it's solved is we have a quantum vacuum, and we know that there can be fluctuations in this quantum vacuum. And on a short enough time scale, you can have extremely massive fluctuations because of these things called the energy time uncertainty relations. It's a bit like Heisenberg's principle, but for a different set. Rather than position and momentum, it involves energy and time. Okay. So if you've got a very small time interval, you can have an absolutely massive energy fluctuation, big enough to create a universe, is the idea. So you can sort of explain, according to Krauss, you can explain why there's something rather than nothing. But any philosopher and I think any person with common sense is going to immediately say, well, okay, where did that quantum vacuum come from? Where did the laws for the energy time uncertainty relations come from? Are they not also some things? Okay, so he's obviously in his explanation, he's starting with some extreme examples of some things, right? An empty space is not nothing, especially if you're talking about a quantum vacuum which has all of this energy. So it's a very very simple-minded way of trying to solve what is a very deep, much larger question, which is, why is there literally anything? Why is there anything rather than nothing?
And then now this is the world. We exist in the world, and then there are things that we can see. And as human beings, we see the what's visible in the physical world is the actions that we take. Our bodies are visible, our actions are visible, right? But then there is also thought. Then there is also feelings, and these are also a part of us, and we are a part of the world, so they're a part of the world, right? So and I don't know if there is a way to measure a word, if there is a way to measure a feeling. We see them act out, and so I don't know what philosophers of physics, specifically if I'm talking to, what they bring to the table regarding these things that are very personal to me. My thoughts and emotions, like they're internal, they're inside me, and in that sense, they're not empirical. I mean, I can prioritize, I can take my decisions based on something, but the reasons that drive me to take those decisions, they're not invariant. They're very prone to changes. They're often changing. So one is that I don't know how emotions and thoughts that we as a race have, right? Let's forget about all other species. The human species seem to definitely have it. And what room has physics made to talk about this? Because we were talking about things which are robust, and they constitute as real things that are, kind of can sustain themselves over a period of time. They're what constitute real. So our feelings and emotions have been around for a while. How they came about, how they've become so sophisticated, I mean, it kind of falls in that realm. I mean, it's strange that why is physics talking about feelings and emotions, feelings and thoughts? But that is also what the philosopher and the physicist is bringing into what they do, right? So, and then I have something else as well. But first, if we can reconcile this.
Yeah, I mean, the usual assumption of a physicist is that anything up there, anything higher up, consciousness, beliefs, thoughts, feelings, emotions, and all of these things will reduce somehow down to physical theories in the final analysis. So the idea would be that feelings are certain brain states. These certain brain states are certain molecular and biochemical interactions. These are reducible to atomic configurations, and so on, all the way down until you get to the base layer, which is supposed to support or generate through emergence everything else that happens in the world. So that's sort of the basic assumption of reductionism, that everything we see is emergent from some fundamental layer. You can call it fundamentalism or sort of physical imperialism or something like that. You don't necessarily have to agree with that, of course. I mean, one of the things I was saying is that physics tends to focus only on
what can be
on empirically observable phenomena. And as you mentioned, specifically those ones that are replicable, they're repeatable.
Yeah.
And so you can detect invariance. But one of the things you don't get in most mental phenomena, even things like economics. Okay, so there with economics, we would think, well, maybe we should be able to get at least close to something like a proper scientific theory. But even economics doesn't really submit to these kinds of analyses where we get law-like behaviors, precisely for the reason you mentioned, that a lot of economic behavior is driven by emotion and feeling. And if you can't map that and have a theory of that, you're not going to get a theory of economics as well. You might get some very broad theory of economics where you're looking at the statistics.
Right.
So usually it ends up being a statistical theory when you're dealing with something that isn't repeatable.
And therefore,
right? You can't tell. Yeah, you can't tell what some act of willpower is going to produce, but you can say things like, on average, there will be this many decisions of this kind and this many decisions of this kind, right? This many buys, this many sells in an economic market or something along those lines. So you have to resort to statistical analyses. And then in that case, maybe you can apply some philosophical methods or some physics methods to it. And in fact, they've tried to do that. There are multiple fields that try and deal with social phenomena using physics models. So there's social physics, there's econophysics, where you're trying as much as possible to dig out the invariant features of economic data. And you forget about, in order to do this, you have to forget about the human side, the individual side.
Individual side, yes.
And you just look at the data as if it was generated by anything else, by any natural process. And then you look for patterns in the data, just as you would do with any kind of system. Obviously, when you do that, you're automatically wiping out essential features, basically, that went into the generation of that data, which are all of the human things. So this is just one of the basic problems with trying to think about things like emotions and will and decisions scientifically. You can never deal with the individual events scientifically. You can only deal with them on average scientifically.
Exactly, I get it. See, because at home, it's me and my husband, right? And what we do is we maintain a daily budget, try to. Okay, and when we're maintaining this budget over a span of a week or usually a month, when the month end, we try to study patterns. Now, this pattern can show us we ate out more than we had. So in our case, we have so if we are eating out, this is our budget, right? This and it's a very amazing, interesting exercise, which is very alive. It's really alive. So we see, okay, so if X was the amount I was supposed to spend on eating out, this time it went up, this time it went down. If so much was to be spent on the dogs, it went up, it went down, whatever. Now, the thing is, it does not stop there. So if the eating thing went beyond what was set for it, the number that was set for it, and we went beyond it, it does not end that, okay, this month we've gone up, next month we should go down. There is a reason why it went down. Reasons like, something in the house, or we were too busy to cook or whatever. So then on an individual level, you can really break it down to the origin of that discrepancy that it leads to. If it leads to a discrepancy, if it leads to matching to what you set out to do, well, good enough. Then to your own person, in your own personal life, you're doing something right. And it gives a sense of peace, having reconciled with the number that you set out to reconcile with, or understanding why you could not reconcile with it. So on an individual level, it makes sense, because when you're doing it on a mass level, which is what averaging out the data is, even if you come down to see patterns, the patterns could be the nation this time went up, the nation this, or a society is, we really get into the why of this happened. And then because it is an individual who's who's a part of the larger world and making happen things that actually happen, in discarding that and then coming to conclusions, isn't it slightly like thin ice territory?
Yeah, I mean, it's the two ways of explaining things. There's a bottom-up way, which is what you're describing, which is why it feels satisfying. When you have a bottom-up description, you are building what happened up from some initial event, and you're looking at the mechanisms that led to some phenomenon, right. Namely, you spent more, you spent less. And that's satisfying because you can see how it happened. You get understanding when you analyze things like this. You don't necessarily get understanding and relief if you're told that on average, this many people spent more in a week. And this is just a law. This is a statistical law that this many people will spend more on their budget within a standard week. That doesn't give you any insight, really. Even though it might be true, it's too high level and too abstract in order to provide an explanation for why it happened. But that's the nature of a lot of scientific ways of explaining. Often you find that it's a law of something, a law of nature or economics or whatever, that is doing the explanation, but it leaves you a little bit, I don't know, it leaves you without understanding of why. Precisely because you can't see the mechanism that led to it, that generated it, right, in the individual case.
Right.
I mean, there are famous examples of these very broad generalizations that don't seem to make that much sense. So, for example, if you look at the mortality statistics, at the number of deaths in a particular year, and the number of methods of death, or the number of suicides, you will often find that it's pretty much invariant, the number of sort of deaths by poison, deaths by hanging, and these kind of things. Obviously, that doesn't give you any information. You can say, well, look, this person hanged himself because this many people will hang themselves, and he was within this class. So it's strange that there's invariance, but obviously there's some underlying pattern, underlying feature that is generating it that would provide a much more satisfying explanation. And without that kind of explanation, you can't also do anything about it. If you've just got the broad generalization, how are you supposed to know how to intervene in something to make things better, right? If you don't know that you've spent more this week on your budget because of these particular factors, you won't know how to tweak things and make things better. So this is why you get a lot more understanding by looking at phenomena in this individual way, and rather than on this kind of high level abstract way.
I mean, even if you look at the level of a collective, so maybe there are some insights to be drawn. So if the number of suicides are occurring, and then maybe, like we were talking about, things being interdisciplinary, right? And then maybe psychology steps in and says depression or not enough jobs. And then you are an individual part of the world, through whatever medium you get to hear this, and you say, okay, I should avoid depression because it could lead to something really, really irreversible. But then the question is, how do you do that? It's easy. One thing to say is simplify your life. Well, how do you do that? Don't be depressed. Well, how do you do that? And that again becomes the domain of maybe philosophy, maybe psychology, maybe just life itself, maybe physics, I don't know. But maybe there is an interaction. The individual makes up the society, and sometimes if my expenses go up, it is also because there is inflation in the country. So the exchange is so much there. The individual, in being reduced to just an individual and not belonging to anyone, loses out on much. Am I right in saying all this? Like, when you're doing it on a slightly massive scale, you lose out on what really are the individual causes that are adding up and causing this, right?
Yeah, exactly. That's what I was referring to. But as you say as well, it's still useful to have the collective data as well, because what you'll be doing, even if you have this more individual approach where you're using psychology on the individual, for example, you will then measure how successful you are being by measuring the collective and seeing how the collective data is changing relative to your interactions at the individual level. Because obviously the collective is just built from all of the individuals. So you need to know if you're tweaking these individual behaviors, your way of knowing has to be at the statistical collective level, that it's working. So there is definitely a place for both, and a place for interdisciplinarity.
Yeah, right. So we were
just on that, actually. just on that, like, so going back to the economics situation, exactly this kind of thing happened. So in order to understand how the collective is shaped, behavioral economics became established, where you're looking at the genuine reasons why, psychological reasons why people make the economic decisions that they do. And having this kind of information rather than purely abstract entities derived from the collective, which is what they were before. They were just these completely faceless, inhuman, Homo economicus kind of creatures. So when you start putting flesh into these creatures, then you can have a far better understanding of how to modify the collective economic features and make a better economy, basically, ultimately.
And again, just taking Mr. Mark Gallagher's name once again for a reason here, he spoke to me about something called infinities, right? And that stayed with me. Infinities. There are multiple infinities between 0 and 1, and smaller infinity, large infinity. Like language definitely fell short, but somehow I've been processing it subconsciously. And what I realize is this: as we are becoming, we are still here. The species is still here, and we have, for the lack of a better word, we've come so far. We've made our lives more comfortable, yes, complicated also, but let's just say we've come so far. We've become a little more sophisticated, unsophisticated in our thinking, but we have come this far. Now, this far, and then our interactions with the world and the world's interaction with us has been also transforming, changing, growing, and adding to what was already there. So this economic behaviors, whatever the term that you just used, now that thing being studied in itself will be so full of its own richness and could go on perhaps forever, till at least we are interacting with there is money involved, there is economy as we understand it as evolved. It is its own infinity. That will be a branch of a study in itself. And as we grow in the next 10 years, 20 years, some other branch might also appear, and simply from our behavior as it acts out in the world. So maybe these are the infinities that those the mathematicians see it in terms of mathematics, that world, the mathematical world, the infinity is there. But if you bring that concept down into reality, when I see my dogs, right, they seem to have a world of their own in which they inhabit as they are, whatever that is, and they'll die. So but they're here as a species. So maybe there is an infinity there. Me as a part of life, as a human being, maybe there is an infinity there, and these infinities seem to coexist. Then do you think this derivation of mine is right? I don't know if it's useful, but does it? For me, it seemed to have reconciled this infinities and infinities, this whole idea that I first heard from Mr. Gallagher.
Well, I mean, so the infinities that Mark Gallagher is talking about are obviously the Cantor's infinity.
That's right.
But in your case, it sounds like you're referring to sort of infinite possibilities, different kinds of possibilities, which are each sort of infinite in scope. So there are ways of analyzing the world and going about the world that seem completely different, but have some sort of infinitude in them. I don't know. Is that kind of sounding right? That basically there's no end to the possibilities in the world?
All I was saying is that the fact I could not understand how infinities can coexist. How can there be another infinity if there is already infinity? Like I don't get it. But then again, if you go back to how one individual was saying that the universe had always been there, right? And there's no big bang, and there's not going to be a big crunch. And then it just suddenly took me to that film, The Matrix. In that, what had happened is a whole world had existed and dissolved at least 6 times before Neo came on. But the world itself, something was eternal. Within it, there were eternities that, I don't know, that materialized and then dissolved. And I don't know if it's still in eternity, but there was an underlying something, what you probably call, I got it from one of your the net of everything. I don't know where I wrote it. The foundational net of things. It was in one of your
Mhm.
lectures that you were giving to the
If you-
musicians.
Okay. Hmm.
So something like that. I'm sorry, I can't remember it now. And I don't know. I made a note of it, and I wanted to speak to you about it. But what are we talking about? So
About the number of interacting infinities, simultaneous infinities.
yeah,
I mean, I don't know, because obviously infinity is a technical term in mathematics. So it's like hard to prove whether something is a genuine infinity.
yeah,
You get the different infinities in mathematics. Obviously, the counting numbers are one infinity, 1, 2, 3, 4, 5, 6, 7. They never end.
yeah,
And then subdivision between 1 and 2, half, quarter, eighth, that never ends. And then there are the real numbers in between those. So you can see how they are leading to genuine infinities. In order to see whether something in the world is a genuine infinity, you need to show that it can be mapped onto one of those mathematical infinities, where you can line up one-to-one what you're talking about in reality and one of these mathematical infinities.
sure, sure.
So there might be some, there might be some scope for that in the kinds of possibilities that are available in a universe. So I think that's probably true. There are often infinitely many ways a universe could go. So I can imagine that being the case. I'm not sure I answered your question properly there.
I don't even know if there was a question. I think we just there was something that was in my mind, and I shared it with you. Got some sense of math is seeing it in a certain way, and if they're out in the life as we experience it, it should be able to map out on whatever math has been able to find out about infinity, which makes sense. So I get that. And
I mean,
yeah.
So one of the ways of understanding. So Mark Balliger probably mentioned Gödel's theorem because you were talking about incompleteness earlier. So he would have been talking about Gödel's theorem. And one of the ways of understanding that is that there is a sort of infinite number of an infinity in the ways things could be. So we might think, one common view is that, of physicists especially, is that once we found the theory of everything, that's it, it's over for knowledge and we know everything. But one of the things that Gödel's theory shows is that there's always a new axiom system that can extend your knowledge and what you think that there is in the universe and can completely change things yet again. So there's sort of infinite freedom, infinite future possibility that comes from Gödel's theorem, even though you might think it looks like the opposite if you're on a superficial reading of Gödel's theorem. Freeman Dyson has a nice discussion of this kind of freedom that Gödel's theorem gives.
Right, and this American mystic, he's no longer with us, Mr. Terence McKenna.
Oh, of course, yeah.
Yes, so he did, because he studied mathematics, like he was interested in physics, and he was always interested in all these higher ideas that all these different subjects and different cultures and religions were putting out into the world. And I think what he was also doing is using these to see what they could mean in life. So for him, I remember listening to one of his videos where he was analyzing what Gödel's theorem could mean. And according to him, his analysis was there's probably never going to be any closure.
Yes, exactly. That's what I was.
Exactly. Yeah. So human beings understand this language. Incompleteness theorem, no, I didn't get it. Too many infinities, no, we didn't get it. But this translation of a phenomena that exists, that has emerged into existence through mathematics, is a part of the real world. We are part of the real world. So maybe there is some commonality, some useful commonality that can be found if you are someone like that, like someone like me, like an idea that has taken hold in math. What does it mean to me? I'm not I'm not a mathematician. I'm not a philosopher of math. I'm a person living out my everyday life. What I would like is to improve the quality of my everyday. So is there something in it? What can I derive from it? So of course you need to have a philosophical, that kind of a mind. Right.
Yeah. Well, I think that way of viewing things of Terence McKenna's is a very good way of putting it, actually. That's exactly the point. People like, so Einstein, for example, Einstein was seeking exactly the opposite of this lack of closure. He thought that there should be a theory of everything. The world should make perfect sense. It should be a closed logical system such that if you alter even the tiniest piece of it, it collapses. So it would be this entirely rigid, perfect system with no freedom, no malleability or anything like this. So that's the exact opposite of this thing that Terence McKenna is describing. But I think a lot of physicists share Einstein's view more than this other view, especially string theorists would also want this closed system where they understand everything and have it all under control. And then that's it, this box, and it's just well understood, and there can be no changes. There's no way of developing it any further, which, yeah, I don't know what you think of that. I don't think that's a very nice sounding view personally.
But do you think this is an archetype?
It sounds like
yeah, but do you think this is an archetype to want perhaps what you're seeking as an individual, and that's why you belong to a community that thinks like that, because you're seeking security, which makes sense. Is that what you're looking for through a unified theory?
I think there's probably a lot of archetypal influences that go into especially people's cosmologies. So there's quite a lot of cyclic cosmologies. There's no reason to have a cyclic cosmology really in the data. We don't really know that the world would be cyclic, but I mean, a cyclic cosmology is about as archetypal as it gets. It's birth and death and rebirth and death. This is like, it's the Ouroboros basically. And yet we find people like Roger Penrose, John Wheeler, a lot of even recent ones actually. There's a lot of cosmologists who seem to be hooked onto this cyclic idea, and I think it's more something from their unconscious than the data. They're not being led to it from analyzing the data. They're being pushed to it from something deeper. Likewise, the ones like Einstein who want this closed system are exactly being driven by this logical perfection archetype. And it probably is a control issue, I think, where they need to have control over the world. Or it might be some different kind of God archetype that's forcing them to see things in this perfect, tightly sort of constrained manner.
I understand. Thank you, Professor Rickles. This was, in my estimate, this was really nice, maybe brilliant. It was, thank you for that. So earlier we were talking about the quantum world. What is it, the existence of a quantum world, does it mean anything to you personally? Has it shifted your paradigm, using a physical phrase?
Well, quantum world, I mean, it's very hard. I mean, look, one of the main things the philosopher of physics is dealing with is the interpretation of quantum theory. And I'm sure that there are very many different approaches that you can give of the quantum world, and what you even mean by the quantum world, that are completely different. Like, this is why I think philosophers, this is one of the key tasks of philosophers, right? We have this theory that's quantum mechanics, that has a certain mathematical structure that everybody agrees on. What they don't agree on is what that mathematical structure means in terms of what kind of world it is representing, because you can have a whole bunch of different kinds of worlds that are nothing like each other, that are all satisfying that same mathematical structure, all generating the same predictions. And yet you've got one in which there's these collapsing wave functions, one in which there's splitting into many worlds, one in which there's this strange non-local pilot wave that's guiding particles around. So you have a whole bunch of different, completely distinct ways of explaining why quantum mechanics works. So my own view is that there's something, that even this multiplicity of worlds points to something a little bit deeper, which is that there's something ineffable about quantum reality. All we have to go on is the experimental results that give us the clicks in the laboratories. We don't know anything about the world, the quantum world, when we're not looking at it. Okay, that's where all the trouble is, right? When we're not looking at it. And John Wheeler, who I like his approach, describes the quantum world as a great smoky dragon, where the tail is completely well defined. That's where you're preparing your experiment. So you know how things are at the beginning of an experiment, right? You've got your double slit experiment, you're setting your apparatus up, and then you know what the world is like when there's a registration and you get a click of a photon on a screen or something like that. So you have two well-defined bits, but then in the middle, there's just this big smoky, ineffable, don't know, thing that we don't know its nature. And I think the reason for that is that we can't know its nature, because in order to know something's nature and get knowledge of it, you need to be able to make a split between an experimental arrangement and a knowledge acquisition, so like a subject. You need to always make a split between an object that you're trying to work out its properties and a subject. And in the state in between, we precisely have a situation where there's no split between subject and object. So we can't possibly have anything. Sorry?
In that space, it merges. There is no split.
It's beyond subject and object. It's non-dual.
Is that what they call consciousness?
Like,
the intervention of consciousness when the thing changes, like what you see on the other end? Yeah.
I mean, that would be one way of making sense of what's happening when we observe things. So this goes back to Niels Bohr, who was one of the creators of quantum mechanics. So he's an interesting guy. He's a bit mystical, actually. So his coat of arms, he was awarded all sorts of honors in Denmark for his work on quantum mechanics. And at the center of his coat of arms, he had the yin-yang symbol, precisely because his view was you need a subject and an object. You always need a split in order to be able to gain knowledge of the world. And in the quantum world, there is never a split. You only get a split at the classical level, and that is what makes the classical level. You have an object, a classical object, and you have a consciousness or some human observer or some record, some way of making a definite record that can be communicated amongst different people classically. But beyond that, you don't have a definite manifest reality. There's no empirical reality in between the preparation of an experiment and the registration of a result of the experiment. So it's genuinely ineffable and non-dual because there's no split. So that's how I view the quantum world at the moment. That's the way I view things. Yin-yang
is order, disorder, right? And then you have those little circles, which means that there is order in disorder, and so there is disorder in order. Mr. Jordan Peterson uses the same example of the yin-yang, and he says because he talks about chaos and order, he says where that curve is, where the two seem to just meet. So I don't know, is that a point where non-duality is about to happen, just like maybe a nanosecond away, but whatever that is, that little curve is where we should strive to be as individuals. So what does that mean to you now?
Well, I think that little curve is where phenomena are created, where the quantum phenomena are created on that little curve. It's where so yeah, I mean, so basically in quantum mechanics, it looks as though there is a creation, a birth of the empirical world from this strange, ineffable chaos. And you mentioned Jordan Peterson, actually. So there's a strange connection to that, of course, which is Jordan Peterson is always talking about dragons, the dragon of chaos. And John Wheeler used as his representation of this strange, ineffable chaos realm where it's neither one thing nor the other, not subject or object. He used a dragon. So there was a dragon. The dragon's head is the experimental result. The dragon's tail is the preparation. Those bits are clear. And then in the middle, there's chaos. And that's a good way of explaining it, that it's undifferentiated. There's no things. There's nothing manifest. And then what happens is when you decide what experiment to perform, that's when you give birth to a result, which is a quantum phenomenon. So, and John Wheeler's view was very much like that. He viewed it as a sort of creation or a birth of phenomena. And the idea is that if you're not asking questions, then you're not going to get an answer from the world. And the questions that you put to the world generate what is manifest by the world.
Yeah.
So.
And there's something very interesting is coming to my mind. I'd like to share with you, and maybe we can wrap it up whenever you'd like to wrap it up, this part of our conversation. So the tail is known, and let's say the face is known. So what remains is let's say the belly, and it's the like Jonah or that in the belly of the whale, and something has to be done there, and then the word question you said, which is also quest, which is what a hero's journey is all about. So all of these things, something that gets into who was this individual, this wonderful person who inspired George Lucas to make
Joseph Campbell.
Joseph Campbell. So he used to speak a lot about this, and I think he also brought in a bit of psychology. There is mythology clearly in what we're saying. Dragons have been around, the killing of the I don't know. So let's not even get there. But I know that this motif has been used a lot, and it just seems to keep coming back up. And then you think of a dragon or a whale. These are all the massive creatures, and we're puny. And but this is where we go to explain whatever it is we're trying to explain. So maybe what we're trying to explain is massive, and but anyway, coming back to this, that it's in the belly where the action happens, which is also where the birth, the conception begins. So there is this
there is definitely something very primordial about it. And what amazes me is how it's not really any further on from what we had 5,000 years ago, where we have stories of the emergence of things from the primordial waters or the cosmic egg or something like that. And John Wheeler, I'm writing a biography of John Wheeler at the moment. And in his notebooks, he's constantly battling with these old issues of what is the nature of this chaos, of this ineffable realm. And he's looking through all of the old philosophers, Parmenides and sort of mystical texts to try and figure out what on earth is the nature of this quantum reality when we're not looking at it. So, and it's a hero's journey. Like his sort of quest is a hero's journey to try and figure out the nature of things as they really are. Yeah. It's good fun. It's a very good book to write.
Nice. Very nice. So is there any last word you'd like to say here regarding what we were talking about, or is this it, and then the second part can happen whenever you're ready?
I think this seems like a good place to stop, and then we can do another one.
My conversation with Professor Rickles was quite a journey. His openness to the mystery underlying the emergence of existence and hope in the human ability to slowly penetrate it felt both reassuring and inspiring. This conversation, like many others we've had on Tattva Deep, further cemented our faith in the common ground shared by the different disciplines of philosophy, physics, mathematics, language, psychology, mythology, and the value they stand to gain by feeding into and off of each other. It will be wonderful to know your thoughts on the interview, and if it inspired your worldview in any way. Thanks for being here. I will see you soon with another interesting mind demystifying another interesting topic. Until then, take care.